Let's look at another example. Here I'd like to write the equation of the line that represents the linear approximation to f of x equals cosine of x at a equals pi over 2. Essentially, I'm trying to write the equation of the line which is tangent to this function at this x value. When we say a equals pi over 2, really that means x equals pi over 2. So I need to find my y value, I need to find my slope. Let's start with the y value. I'm going to take pi over 2 and plug that into f of x. So I'm looking at cosine of pi over 2. Cosine of pi over 2, though, that's just 0. So there is my y value. Next, I need the slope of the tangent line. Well, slope of the tangent line is given by the derivative, f prime of x. So here, f prime of x, derivative of cosine of x, that is negative sine of x. And now I can take pi over 2 and plug that into my derivative. Oops, f prime of pi over 2, negative sine of pi over 2. This is equal to negative 1. And this represents the slope of my tangent line at pi over 2. So I have my x value, I have my y value, I have my slope. Let's write the equation of this tangent line. So y minus my y coordinate is 0 equals m, that's negative 1, times x minus my x coordinate. My x coordinate is pi over 2, so this is y equals negative x plus pi over 2. Now, even though this is our linear approximation, this is L of x right here, it's still not a completely nice function to work with, particularly because we have to deal with this pi over 2. But if we compare that to what we might use it to approximate, so here I would like to use it to approximate cosine of 1.6. In other words, I'm trying to estimate, not f of 1.6. I would like to, I would like to approximate f of 1.6. And f of 1.6, this is going to be approximately equal to L of 1.6. So I'm going to look at cosine of 1.6. This is approximately equal to L of 1.6. I'm going to take 1.6, plug that into my linear approximation, and use that to estimate cosine of 1.6. Now earlier we said, hey, this is not the nicest to work with, in particular because of the pi over 2, but I can estimate pi over 2. I don't really have any great way to estimate cosine of 1.6. I know that 1.6 is close to pi over 2, but there's no great way for me to know what that is unless I use this linear approximation. So here, L of 1.6, this is equal to opposite 1.6 plus pi over 2. So let's see, L of negative 1.6 plus pi over 2. If I look at negative 1.6 plus pi over 2, here you will have to use your graphing calculator to get a good answer. I end up with negative 0.0292 if we round to, let's say, 4 decimal places. So this is my approximation. I believe that this is fairly close to cosine of 1.6. So here is my approximation, negative 0.0292. And if you have your calculator in radian mode, you can type in cosine of 1.6 and see, I get negative 0.29199. So we are awfully close here. Some of these problems will also have you computing the percent error in your approximation using this formula. So here I can actually use, or I can find the percent error that I have in my problem. Ideally, I'll have a low percent error, because if I have a high percent error, that means I'm very wrong. So here, if I want the approximation, so I would use my approximation. This is negative 0.0292. This is the value we came up with here in our linear approximation, minus the exact value. And here you'll want to use a graphing calculator, but here I have opposite 0.02929995. I'm actually going to go, or excuse me, I missed a decimal here. I'm going to go a little bit farther out because if I round to 4 decimal places, the percent error is 0, and that's not a great look here. Divided by the exact value, which we said was opposite 0.0291995. And let's see. I have opposite 0.0292 minus 0.0291995 divided by negative 0.0291995 gives me, I have 1.7 times 10 to the negative 5th. In other words, this is 0.00017. And that's not even the percent error. I need to take that and then multiply that by 100. That's something I didn't do here. So if I take this value and multiply it by 100, if I multiply this by 100, it would just slide the decimal place to the right by 2 places. So 0.0017%. That's an incredibly small error here. We are awfully close to the exact value here. We're less than 1%, less than 0.5%, less than half of a percent. So we are very, very close. This is very good news for us. The lower this percent error is, the more accurate our linear approximation is at the end of the day.